Cool. Okay. Right. So again, feel free to interrupt me if you dare unmute yourselves, or because you can, right? Yeah, someone spoke to you. Okay, let's get started then. Right. So I hope I got the right exercises. But if I recall correctly, the first problem was problem 1. So this is my first time using an iPad, by the way, so let's hope it goes well. We need to construct a term of the following type. So there's a big pi type, right? So we had first it takes 2 arguments, x and y in A, a path or an identity proof P, proving that x is equal to y, and a proof Q that y is equal to z, and produces a new proof that P composed with Q inverse is equal to Q inverse composed with P inverse. Thank you. Yes, absolutely, I should. Okay, let's try this cool thing. Wow. Oh, okay, that was too hard. X, Y, and Z. That's right. Okay. So the idea here is that we're going to use, so I hope this notation makes sense to you. I think Paige mentioned composition and path inversion, right? The idea now is we're going to throw path induction or the identity elimination on this guy, just completely destroy it with identity elimination. And that's, you're going to see this a lot in this course. So I want to give kind of an informal proof, because I know you've been seeing all these proof trees, but it's nice to see how we actually reason in type theory and in homotopy type theory in particular. So let's try to solve this. So let's try to sort of write out explicitly what we have to do. So let's assume that we are given the following data. So we're given 3 points, x, y, and z in A. We're given a proof, given a proof P that x is equal to y. And we are given a proof Q that y is equal to z. And we want a proof or a term of type P composed with Q inverse equals Q inverse composed with P inverse, right? Because that's precisely how you construct something of a pi type, right? You introduce the arguments. X, Y, and Z. You introduce P and you introduce Q, and you produce a term of this guy, right? Okay. Well, this is super nice, this situation now, because we have 3 points here. And in particular, we have a path P from X to Y. Well, whenever we have a path between 2 different points, or an identity proof, an identification, I should say, I think is the terminology they used, we should, well, immediately see that, wow, this is a perfect opportunity to apply identity elimination or path induction. So that's going to be our solution. So well, let's try to, I'm so sorry, I'm really not used to iPads. Okay, that's our data. So now we solve this by apply identity elimination on P, right? So what happens then? Well, this first, what this is going to do is this is going to completely delete Y from the above scenario. So Y is going to be replaced everywhere by X. So this replaces Y by X. And also P gets deleted and gets replaced by REFL, by the reflexivity path, right? So it also replaces P by REFL X. Okay, so now we get a new problem. New, I could say, call it a reduced problem. And this is going to be the same problem as we started with, but nicer. So let's copy it. If I can do that. Whoops. Oh, no. Shit. I'm sorry. This is going to take a little time for me to get used to. I tried yesterday and it went well, but not today. If we do it like that, duplicate. Aha. Okay, so we're given a new problem, but in this new problem, the Y is completely erased. The P is going to be gone because it's replaced by REFL everywhere. So we're just going to delete the P. And well, Q is no longer a path from Y to Z. It's a path from X to Z. And the thing we're now trying to prove is not that P composed with Q inverse equals Q inverse composed with P inverse, is that well, P is gone now, right? So now we just want to prove that REFL composed with Q inverse is equal to Q inverse composed with REFL inverse. Okay, now this problem here, it's, well, we're not quite done yet, but it's easier because, well, we have less data to worry about. Okay, but now let's do the same thing again, because now we see that Q is a path or an identification of X and Z. So, well, we can apply path induction or identity elimination on Q as well, right? Okay, apply. So now apply identity elimination on Q. And we get a new problem again, because what happens now is that, so let me try to copy this again. Truth, and truth. Oops, sorry. That didn't go too well, but not too horribly either. If we apply, oops, do you have to do path induction on Q, or could you say? So the issue here is that when you define composition, right? So what Jacob asked was, aren't we done here? Because REFL composed with Q, that's just Q, and Q inverse composed with REFL inverse, that should just be Q inverse. The issue here is when we defined composition of path of proofs, we picked which side to do the induction on, right? So when we defined composition, we defined it, I think what Paige did at least, was she defined it so that if you compose with REFL on the left side, it reduces. So actually, I mean, you're right, this is just Q here. However, if it, with composition on the right is still undefined, because when we defined it, we only did it on the left. So this, we don't know yet that this is just Q. You can prove that it's just Q, but you need path induction. So that's essentially what we're going to do now, actually, because well, that's the goal. Okay, you got it? Perfect. Oh, and now there's a line appearing here. I'm so sorry. It's so embarrassing. So what is we trying to prove again? We're trying to prove, right? Okay, sorry. Okay, so now let's apply path induction on Q. Well, when we apply path induction on Q, the Z just becomes X. So we have no Z anymore. It's deleted, gone. So maybe let's do it like this. So now we just have a point X in A, and we have an identification from X with what? Well, sorry, with X, right? Because Z became X everywhere. But also this Q, when you apply path induction, it becomes nothing. It becomes REFL. So there's no longer a Q here. There's just REFL of X. So actually what we're trying to prove right now is the same thing as above, but with Q replaced by REFL everywhere. So now the new goal is just proving that REFL X composed with REFL X inverse is equal to REFL inverse composed with REFL inverse. And now things reduce, right? Because when we defined path composition, composing something with REFL on the left, well, it just reduces. It just deletes the REFL on the left. So actually, this thing in here is just REFL. Well, we still have an inversion, right? On the outside. But when we defined inversion, we also defined that by path induction. And the REFL case, what was inversion of REFL? Well, inversion of REFL is just REFL again. So actually the left-hand side here is literally, it's definitionally equal to just REFL. But the right-hand side, well, you get the same thing, right? So REFL inverse, that's just REFL. So this whole thing is just REFL composed with REFL. And well, I just said that REFL composed with REFL is just REFL. So actually this is literally just REFL. So now our new goal is proving this thing, that REFL equals REFL. If we did it formally, we would have a bunch of app of inversion, right? For which part? So actually, you don't need to use app for the inversion at all. You could have done this whole thing using app, but the things I'm saying now, everything I've said in this part is just definitionally. Ah, I see. Well, so yeah, well, it's kind of app, right? But the thing is that REFL composed with REFL, the thing that you have inside, before you actually care about the so what you do is you evaluate what's inside the inversion first, and you see that that's literally just REFL. So actually REFL composed with REFL inverted literally reduces to REFL. It's just unfolding all the definitions. So those would be the computation rules for equality. Yes, exactly. We have app for definitional equality for free. That's a great way of phrasing it precisely. Well, it's for free. I mean, these they are computation rules, but the computation rules basically say that we get app for free. Yeah. Yeah. Okay. So now we need to prove that REFL is equal to REFL, but that's not very hard because we have, of course, our favorite term, REFL of REFL X, which is a proof that REFL X is equal to REFL X, and we're done. So you see, that's really how you reason in HoTT. Unfortunately, things become complicated the more you work with HOT, but trying to use path induction is always going to be your sort of go-to tactic for solving any problem concerning paths or identity proofs. Okay, you'll see a lot more of this stuff later. Let's continue with the second problem. The second problem I think was a bit different. So I'm very scared now because I think I have to be a bit formal here. Let's see. This was more of a traditionally phrased problem. Can I find the problem? Yes. Okay. So the second problem was this. So problem 2. How am I doing on time? Okay. Problem 2. We define the projections. Sorry, I should really say what these things are before I do this. Sorry. Let's start. Too fast. Okay, so let A and B be two types. Now we can define the product of A and B. So what's a product? Well, it's just going to be points, pairs of points in A and in B, right? We can define this to be a sigma type consisting of points in A together with a point in B, right? So usually you'll see this written something like B of X here, right? The idea here is just that B is constant. So it doesn't matter which X you plug in, B of X we define to be just B. It's constant B. So I can write it like this. I hope this makes sense. Please tell me if it doesn't. Right. So we have an elimination rule for product. So, and it says that, I'm going to skip all the gammas in all the contexts because they're annoying, but they're there implicitly, okay? So given a Z in A times B, let's say that we have a type D of Z, and let's say that given a point A in A and a point B in B, we have a term D of type DAB. Then we define product elimination to give us the following. So we're given a Z, Z in A cross B. We get a term ind of dz of type dz. So what is this elimination rule saying? Well, it says that in order to prove something about products, we just need to do it for the terms on of this form here. So you can always assume, given a point Z in a product, you can always assume that it's on the form A, comma B for some A in A and B in B. And it literally just says that, well, the product of two types is just literally points in A together with points in B. That's precisely what the elimination rule says. Okay, so what's the actual problem here? The problem is to define the projection maps PR1 from A cross B to A and PR2 from A cross B to B using XLIM. Okay. Right. So how do we solve this? Well, let's move this guy down a bit. See if I can do this. It's so hard, but maybe if I'm strong. Yes. Let's place it here. Okay. Hopla. No, 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 no. So there we go. Okay. Right. Maybe I should show the problem too. All right. So let's just do one of them, okay? Because it's going to be exactly the same for the other one. Right. So if we want to apply, what is it we want actually? So we're trying to define something of the form. Let's do PR1. So we want a term PR1 AXB to A. So how do we define a function? Well, we introduce something of term A cross B, and we want to be able to produce something in A. Okay, so let's assume that we have a Z in A cross B. We want to define PR1 of Z in A. Okay, so the goal now is proving that we have something in A. Okay, and we want to use product elimination. Well, the only reasonable thing, if we want our product elimination to end with something of type A, is to set this D of Z here to just be A. Okay, so we're going to define D of Z for any Z. Maybe it was bad that I called it Z. Let's call it D of X for any X to be just A. Whatever you plug in, it's always going to be A. Okay. So let's try to imitate the the rule here. This rule. Well, let's try the first line here. Given a point Z in A cross B, well, we certainly have that A is a type, right? Okay, so we have the first line. What about the second line, this line? So given a point A in A and B in B, we want to produce something of type DAB. Well, DAB is just A again. So we want something of type A. Well, we have something of type A already, an A. So let's just plug in that one. And we're done, because now we may conclude that for any Z, sorry, it's too fast. For any Z, in A cross B, we have a term int X of A Z of type A. And we take this term here to be our definition. We're going to define PR1 to be precisely this. And that's it. And for PR2, the second projection, you'll do the exact same thing. It's just that you replace all the A's by B's. Okay. I hope that made sense. It's very likely that I made some mistakes somewhere. I'm not very good with this formal stuff, but hopefully I didn't. All right, but there was a second problem here. So, well, what should I call it? Problem 2, let's call it 2B. And what was that? Well, that was use XLIM to get a term of the following type. So pi z a cross b, z is equal to the pair of PR or P1 applied to z and P2 applied to z. Okay, so I hope you see what this is saying. So this is saying that if you take a point z in, we would use XComp rule to prove that. Precisely, yes. So actually, I can mention this. So I got a question now saying that we would use, well, the question was precisely, it's a good question, so let me write it out in its entirety. We would use XComp to prove PR1 of AB equals A. Actually, so this is a definitional equality even. So it's definitionally equal to A. And that's precisely right. And this is precisely what we're going to do. So that's good. Let me give a little, circle this in green here. Just, okay, that's good. This is precisely the approach that we're going to use. Sorry. Right, but I hope you all understand what this is saying. So it's saying that if you're given a point in A cross B, and you just look at the first projection of that and the second projection of that, and you pair them up, then that's equal to the point that you started with. So it's saying that, again, that everything in A cross B is just a pair of two things, right? Okay, so now we're going to use this good comment I got here to solve this. Okay, so what do we need? Solution. For every z in A cross B, we need a term of type z equals PR1z, comma PR2z. Okay. Okay, let's apply first. Apply what's it called? XLIM. So what XLIM tells us is that z is always going to be equal to a pair of points. So XLIM tells us that z is literally just A comma B for some A in A and B in B. Okay, so we have a new goal. And the new goal is proving that A comma B is equal to PR1 applied to A comma B and PR2 of A comma B. But I just got a nice comment stating the fact that PR1 of AB, by the computation rule for products, which I didn't introduce, but it's actually just the computation rule for sigma types, because we actually defined the product to be sigma types. This is literally just A. And PR2, we didn't define PR2, but I promise you, since you're doing the exact same thing, it's completely symmetric, this is literally just going to be B. So this is definitionally equal to A and B. So actually our new goal is just proving that A comma B is equal to A comma B. And what do you know? We have a term of that type, REFL, AB. And so we're done. So you see, I'm very quick to get it. If I see an opportunity to get it informal, I'll be informal. But this was still kind of formal, I thought. I hope this made sense to everyone. If not, please tell me. Now I think we'll be dealing with more paths. Okay, I'm confused. I'm confused by z equals a comma b for some a b. Isn't that what we're trying to prove? Maybe I did that a bit too quickly. So the idea here was that, oh, sorry, where is that? That's this is our elimination rule. So let's try to spell this out. Yes, precisely. Yes. So what I did was I replaced z everywhere. I just forgot about z and replaced it by a comma b for some arbitrary a and b, right? Because that's kind of precisely what the elimination rule tells us. It tells us whenever you need to prove something for any z in a cross b, it's always enough to assume that z is equal to a, this guy, a comma b for some a and b and b. So that's the intuition you should have for this elimination rule. It tells us that whenever you have a z in a cross b, you can always replace it by some arbitrary a in a and some arbitrary b in b. I hope that makes a bit more sense. You could, of course, be much more formal than I was here and write out the full tree, but then I'm worried that I would probably confuse you even more. Is that okay? Okay. So if we would use sigma the computation rule for sigma, what would d be? Oh crap! Then I probably need to look up how you define the computation rule for sigma in the lectures. But that's something I should actually look at. Give me 1 second. Well, I mean, it's going to be the same thing. I mean, so the dependent type D here, what we were trying to prove was Z equals PR1 of Z, comma, PR2 of Z, right? Oh yeah, oh, the first thing I said. Oh, sorry, I thought you meant, okay. Sorry. I'm really sorry to people watching this recording after. I'm confusing the questions. Yes, for PR1, that would just be, for the first prediction, the D would just be A. Yeah, I thought you meant for the second problem, what D would be. But no, of course not. We're not even using sigma computation. Yes, William is right. I mean, yeah, so what I'm saying now that you can always replace any z by a comma b. This is sort of a, I don't want to use any fancy words now. You can't prove this. In general, it's just sort of a heuristic, right? I mean, the computation rule just tells you that whenever you have a type depending on z, it literally says that actually. I mean, you can always replace z by a comma b. So it's kind of hard to state this in general in any way better than it's already stated by the computation rule. So the computation rule kind of literally tells you this fact. But I'm worried I'm confusing everyone. Because I hope it's okay. If there are any confusions, I'll stay after the lecture and we'll talk about it. Now, where did my exercises go? What are we doing now? Oh, sorry, 1 sec. Yes. Okay. This question I like because it starts with informal. So problem 3. Problem 3. Not the third projection. Problem 3. Give an informal. So I've kind of, this was my idea. I warmed you up for this one, with the whole informal business. Give an informal construction of the following type. So here's a big type. So pi a prime in A, B and B prime in B, A equals A prime, cross B equals B prime to A comma B. Now this is in the pair type. Equals, I can index this here just to state clearly which type we're working over. A comma B is equal to A prime comma B prime. I'm sorry, I got a bit tiny there. Okay. Okay. So we're kind of just wanting to prove that we're trying to sort of understand how identifications in the product type work. Yeah, this is kind of the problem here. Okay, so this is a big type, but it's just a big pi type, right? So we have a bunch of nice arguments that we can introduce. So let's solve this. Okay, so the first pi type says we have an A and an A prime in A. Okay, so we're given an A prime in A. We are given a B and a B prime in B. And then we're given some Z of type A equals A prime cross B equals B prime. And we want a proof or a term, let's just call it T, of A, B equals A prime, B prime. Okay. Now that looks much less scary than the big pi type, right? Okay, so we have this Z here. This Z looks nice. It's telling us something about A and B, right? But now the Z is an arbitrary element of some product type. We will want to use the projections, right? So in the previous exercise, we defined the first and second projection. Sorry, actually, I don't want to do that. That's a bad idea, introducing the projections, because I'm going to kind of tell you a lie if I do so. So let's do it in a different way. Let's kind of repeat the projection idea from the previous exercise. So let's apply the elimination rule for products on Z. This tells us that Z may be replaced by P comma Q for some arbitrary P of type A equals A prime and Q B equals B prime. And that's nice because now we actually have these two guys explicitly. Okay, so let me rephrase the whole problem again, as I always do. All right. Now the new problem is not precisely this, but this. Oh. Now we can forget about Z and just use P and Q everywhere. So now we're given A and A prime in A, B and B prime in B, and we're given a proof that A is equal to A, and a proof that B is equal to B prime. And we still want something of this term. That hasn't changed. There was no Z appearing in there. It's the same as before. Okay. Well, now it's time to apply path induction, right? So apply. I shouldn't call it path induction. I don't know if you call it path induction in the lecture. I don't remember. I guess she probably did by mistake. But let's apply identity elimination on both on P and also on Q. P and Q. So what happens then? Well, what happens when you apply path induction? Well, let me do this cool thing again. I'm so happy about this pen I got. I think it's so cool. Wow. Okay. What happens when you apply path induction? Well, first of all, why not call it path induction? Well, of course, I love path induction. It's path induction to me too, but it kind of suggests that there's some topology going on here. And I don't know how much of the topological stuff you've talked about. And in particular, I don't know how much of the topological stuff people understand. But yes, path induction, you should remember path induction. Of course, it's the best word. It's the best thing in the world. Right. Okay, so after we applied identity elimination or path induction on P and Q, what happens now is that this P here is no longer a path from A to A prime, because when you apply path induction on P, A prime gets identified with A. So all the A primes are gone. And the same thing here with the path induction on Q, all the B primes are gone. So now we only have A and B in our context. And these two paths, P and Q, they're also gone. So let's just delete them because they both get replaced by REFL. So now our new goal is no longer this, it's this. We want a term T of A and B equals A and B. Well, that's quite easy if you give it directly. It's just REFL AB, and we're done. See, path induction works. Hopefully, as I always say, everyone understood. Tell me if something was weird or if I made any mistakes. Otherwise, I'll continue. I'm actually going to have a sip of coffee first. Oh, that's very cold. Okay. Problem number 4. This one is good. Good problem. I like this. This is one of my favorite types. Okay. So let's assume we have a type A. And a point in A, we just call A, little a. Let's fix these two things. Okay, they're in our context. We have them. They're fixed. Let's consider the type. Consider the type sigma xa A equals X. So what is this type? Well, this type consists of pairs. So it consists of pairs. And pairs of what? Well, pairs XP, where X is a point in A, and P is a proof or a path from X to from A to X. Okay. Now here's another fact. we can produce a point of this type always. So in order to produce a point, so there is a point. There's a point here. Funny, right? And the point is A, comma, refl A. Well, because I told you that this type consists of first a point in A and a proof that A is equal to this point. So if I just pick the first point to be A, well, then I might as well pick the path to be refl. Okay. So we always have a point of this type, but it gets even nicer. So here's the problem. Show that for any other point, Z of this type, we have that, oops, we have that A comma refl A equals Z. So this type not only has a point, but what we're trying to prove is that it has a unique point. So in homotopy type theory, this would be called a contractible type. It consists of precisely one point. How do we prove this? Okay. So solution. Let Z be a point of this type. Well, kind of annoying to call it Z, you know, Z really is a pair, right? So by the sigma elimination rule, we know, or I shouldn't say know that, but we may set Z to be just a pair. A is already taken. Another good name, B, maybe, yeah. B, P, where B is another point in A, and P is a path from X to Y. Okay. So after we do this, the new goal is now proving, shouldn't it be P? Shouldn't it be P? Ah, yeah, but you're right. You're right. This is, yeah. Thank you. Oh my goodness. So I have some old notes. I wrote up some notes yesterday and I'm following them, but using different notations. It's a genius move from my side. Thank you. That's right. Yep. Thank you. Okay. So the new goal is to prove that A comma refl A is equal over this sigma type to B comma P. Well, we have a path P between 2 points. The endpoint is some random B. Path induction, right? Always path induction. So apply, I'm still gonna call it identity elimination. So let's apply identity elimination on P. What happens? This replaces B by A everywhere, because A was the starting point. and it replaces P by refl A. Aha. So new goal, proving that A comma refl A is equal to A comma refl A. That looks nice because there's always a term of this type, namely refl of A comma refl A. And we're done. See how easy everything becomes with path induction? It's amazing, right? I could go on and on about this type because this type is very important. You can sort of say that any good identity type should satisfy this fact that it's contractible. Do we have to be careful whether we apply regular path induction or based path induction because one endpoint is fixed? Aha, that's a good question. I am kind of agnostic to which rule we choose to use. So as long as one of the endpoints is not fixed, induct away. That's all that matters. But that's important. One endpoint has to be free. It has to be an arbitrary one. So we'll mention this later, well, very soon. There's just one exercise first. Yeah, precisely. Yeah, normal path induction works here. Yeah. Okay. So you remember before I wrote the concatenation of two paths, P composed with Q. So now in this new exercise, we're going to give this a new name. Okay, so exercise number 5. Whoops, problem 5. So we have a function. Concat 1 from pi x y z, which takes a proof xy and a proof yz and produces a proof x equals z. Okay. Now this function concat is literally just so concat of x, y, z, p, q. We just define this to be p composed with q. So it's our good old composition function. It's concat 1. So now the problem is give two different constructions of let's call them let's give two different constructions, concat 2 and concat 3 of the same type. So essentially, we're being asked to give new definitions of path composition. Okay. So I hope I remember right now that in the previous lecture, they defined path composition by using path induction on the first argument. So P composed with Q is defined by refl composed with Q. But we can ask ourselves, what happens if we apply path induction or identity elimination on the second argument instead? So we're given X, Y, and Z in a path P from X to Y, and a path Q from Y to Z. Okay, let's call this concat. Now we're going to define concat 2. We want to define something of type. We want to define concat 2 of X, Y, Z, comma, P, Q of type X equals Z. Okay, that's what we want. So what we did first time in the lecture, I think, was that we used path induction on P, but why not do it differently this time and apply path induction on Q? So apply path induction, identity elimination on Q. Yes, yes. So someone solved the concat 3 case. I'm getting there. Thank you, Lambda Duck. That's precisely it. Applying identity elimination on Q, so that tells us that it suffices to define concat 2 of X, Y, and Y of P and refo Y. And because we applied path induction on Q, which was a path from Y to Z, the Z disappears and gets replaced by Y. So this time it's going to be of type X equals Y. Well, we want to define something of type X equals Y, but we have something of type X equals Y, P. So let's just define this to be P. And we're done. So we use path induction on the second argument this time, and we defined essentially P composed with refo to be just P. So this is a different path composition than before because it reduces differently. So the previous one, if you take refo composed with P, that would reduce to just refo. To just P immediately. This time, if you take P composed with refo on the right-hand side instead, it will reduce to P. So there's a difference here, you know. You can choose whichever one you prefer. They are going to be the same in the end, but okay, so that was concat 2. But you know what? Let's stay in this setting because concat 3 we're given the exact same data, right? So to define concat 3, we will also do this path induction on Q, so that we end up in sorry. So for concat 3, if we apply path induction on Q, we also need to produce something like this. But now what we can ask, well, we can continue doing path induction because we love path induction so much. We can just apply path induction again on P. So we're going to define concat 3 by a further path induction on P this time. So concat 3 will be defined. So it suffices to define concat 3 for X, 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 and refo X, and refo X. And this is going to be something of type X equals X. well, want to produce something of type x equals x, we just define this to be refl x. Okay, so this is concat 3 is a really kind of a shit way of doing it, because we're just applying way too much path induction. I mean, again, path induction is great, but if you apply it too much, things won't reduce. So for example, concat 3, if you take refl composed with p using the concat 3 definition, that won't reduce to just p. That will remain as refl composed with p. Question, does the order of eliminating on both p and q matter here? Do the two versions of concat 3 behave differently? Aha. So yeah, we could have, so what I did now is I started by inducting on q and then on p when I constructed concat 3. I could have started with inducting on p and then on q. But yeah, no, they will be defined in the exact same way, because they're really defined by the refl case. That's really where the magic happens. So yeah, in practice, they will be pretty much the same. They will be equally unusable. I mean, of course, they're usable, but annoying to work with. But yeah, the computation rule only governs the refl case anyway, so it's really when we've done it the full. So it doesn't really matter which order we do it in for concat 3. Okay, and that's it. Now we have our functions. So now the second problem here, it's a problem 5b. Prove they're all the same. So in particular, what we want to prove is, given x, y, and z in A, p from x to y, and q from y to z, we want to prove that concat 1, x, y, z, p, q, oof, this is going to be annoying to write, is equal to concat 2, x, y, z, p, q is equal to concat 3. So this is a bit informal. Now I'm writing a triple equality here, but I'm just saying we want to prove that they're all equal. Okay. X, Y, Z, P, Q. Okay. But this is not too hard, because we have two nice paths that we can use path induction on. So when we prove this, we just apply path induction. Oop, no, I've been calling it identity elimination, sorry. On both P, P and Q. It doesn't matter which order you do it in this case. So we apply identity elimination on both P and Q, and this is going to completely delete P from the equation, completely delete Q from the equation. They will both be replaced by refl x. So after doing this, suffices to show concat 1 x x x refl equals concat 2 x x x refl concat 3 x x x refl x. But now we can use the computation rule, right? So what was the definition of concat 1? Well, concat 1 was just the way, I mean, this was refl composed with refl, right? And this is definitionally just refl. So the first line is literally just refl. And in the second case, well, we did it the same way, just that we started on the left, on the right-hand side instead, but it's still going to reduce to just REFL. So if you want to check this, you can sit down and do it more carefully than I'm doing it here, but I promise you, this will just, the second one will also reduce to just REFL. Because the first one, what it does is actually when you have REFL in the second argument here, it just projects the first path, which was REFL. And the second one, the way that we constructed this, was that when we have REFL in the first argument here, it just projects the second path. So both concat1 and concat2 are going to be strictly just REFL. And concat3, well, we defined it only for the REFL case, right? Our definition was just REFL. So this is also just REFL. So all three paths are actually REFL. All three are just REFL. So they are equal. And that's it. Okay, I hope that makes sense. Okay, I don't know how long these exercise sessions usually are. I have one last problem that I'll do, and then someone maybe tell me, are they usually 1 hour or 1.5? I want to remember 2 hours, maybe. No, maybe I'm going super fast. Usually 1. Oh, I'm going super slow. Okay, let me do one more then. If you have to go, I forgive you. All right, okay, perfect. All right, problem number 6. This is a fun one too. So this is, we're going to try to prove something false. Okay, so let's say that we have a point A in A. The problem is try to prove, sorry, I shouldn't say, try to construct a term of type pi t a equals a, p equals REFL a. So in other words, prove that for every p a equals a, we have p equals REFL a. And if this doesn't work out, if hard, it should be hard because it's false. If hard, what goes wrong? So the point of this exercise is to show you a scenario when you cannot apply path induction. Okay, so let me give you an incorrect solution. And we'll try to spot where the error is. So we're given a path P from A to A, and we want something of type P equals REFL A. Okay, so please keep in mind this is incorrect, but what we would usually do is just, okay, well, we have a path from between 2 points, apply identity elimination on P. This replaces it by REFL, right? So P gets replaced by REFL. So it suffices to show that REFL A equals REFL A. So if someone spots the error, please type it in the chat or something if you want to. You don't have to. But here we're done. Because, well, REFL A is of course equal to REFL A. So we prove this by REFL of REFL A. Okay, so I got a comment here. The rule for path induction requires a context like A in A, B in A, B, A equals B. And there's no obvious way to extend this to a context like A in A, P of A equals A. Precisely. So this is not correct because we were not allowed to apply path induction here. And the point was that this second argument here, the A here, the endpoint, is the same as the first point, definitionally same as the first point. Whenever you want to apply path induction, you need it to be of this form, P, oops, let's do black. P of A equals B for arbitrary why can I not duplicate A and A so that I have the context? Okay, so that was a good question. So why can't we just do, well, the rule for elimination says AA, BA, it starts like this, right? P of A equals B. So why can't we just, well, replace this B by A here and write AA and just duplicate A? It's of the same form, right? So the rule here, maybe they didn't mention it, but this has to be fresh. This has to be a new one. So we're actually not allowed to do it this way. So this is going to make a lot more sense to you later when you see univalence and these types of things. Then you're going to be able to prove that this is actually false. We don't really have the tools yet to prove that it's false. But the idea is it always the case that variable names in a context must be distinct? Ooh, oh, let me think. For all the rules I have in mind, they are distinct, but maybe there's a case where they're not. No, but you can certainly duplicate things, right? Can you? I think this really depends on your system. But this is really not my area. I'm very sorry. I'm really working inside of type theory. I haven't worked much with the logical parts of type theories. That's a very good question, but yeah, sorry. I don't want to lie, especially since I'm recording. I don't want to lie. But it certainly seems possible to enforce that rule. But at least in this cases, you have to allow for the second point to be arbitrary. Yeah, so Matthias is right. Yes. Okay, so I mean, what we could do, so if we want, we really need something of this form, right? So in order to, oops, in order to apply path induction, or yeah, elim, I can informally read it as if for all A, B in A and A equals B, then yes, precisely. Yes, precisely. You should be able to do it for all. Well, for all, yeah, it's tricky, right? Because another case where it doesn't work, so say you might have something different. You might have a path like this. Oops. but it's kind of true what you're saying. You should, there's a good idea to have, but you could have something like P of A equals to say F of A, where F is a function from A to A. In this case, you're also not allowed to use path induction because the A appears in this term, right? So you really need the second term to be just a fresh variable. But I think your intuition is right, Matthias. Maybe I also misunderstood a bit. It looks like you're right. Right, but we can, let's try to solve this problem anyway, and let's try to generalize it. So in order to generalize it, if we want to be able to apply path induction, because we will certainly need to apply path induction in order to prove something like this, we will need to generalize it. Yeah, maybe doing the path induction more formally using the rule explicitly would help clarifying. Yes, maybe. Okay, let me try this. God damn, you like to be formal, huh? You know, when I did both my bachelor's and master's, I was in logic. Then I loved doing this stuff, but now I've forgotten all about it. Okay, let me try. So we're trying to prove. So we're trying to prove that A, we have an, oops, A in A and B in. So what does the rule say? It says that if you have an A in A and a B in B and a path from A to B, and you have a type B of A, B, P, and you have a proof. So for A in A, you have a proof D of D A referral of A. Then you have A in A and B in B and P. Sorry for my handwriting, my goodness. B in A equals B. You have a term of type B, A, B, P. Is it right? Oh, thank you. Yes, yes. Let's thank you. Oh my goodness, it should absolutely include a D. A, B, P. Maybe this is not exactly what they wrote, but yeah, let's include as much as we can. D, A, B, P. That's all the data. Okay. Right. So in order to prove something, if you want to use this principle, okay, let me give it a name to it. So the first step is important, right? So you want to use path induction to prove something, right? That's going to be the first step of formalizing this idea of proving something is to be able to state which type you're actually trying to construct a term of. So, and what the this should be an A. Sorry, I'm so used to using lowercase letters for. I'm very sorry. So, we need to make sense of this first line here. So we need to state the theorem we're trying to prove in terms of some arbitrary A and some arbitrary B and some arbitrary path P. Okay, and the issue here is that we're trying to prove for any A in A, well, and sure, B in A, but that's implicit. And P, so we can just remove it. Sorry. P from A to A, our term D, or sorry, of our type D will is just P equals refl A. This is problematic now because if we want to generalize this, what we would need to do is we would need to say something like this. We would want to define for A in A and B in A and P, A equals B, we would want DAB to be P equals refl A. That would kind of be the only way to prove this. But can you spot the problem here? Exactly, this is not a type corrector. This is not well typed. So P equals refl A, it doesn't work. We can't form this type. Because on the left-hand side, we have P, which is of type A equals B. And on the right-hand side here, we have refl A, which is of type A equals A. So forming the type P equals refl A, and that's impossible because, let me clarify this by like so. That's impossible because the left-hand side and the right-hand side belong to different types, so we can't even form the equality. So there's no good way of kind of generalizing this this idea. And thank God, because that's kind of what gives rise to homotopy type theory. Now I'm going to babble a bit. So I mean, I mean, my intuition for, because I know Paige mentioned a little bit about these sort of topological intuitions here. So my idea, why doesn't path induction work when you have something of P A equals A? Well, remember this idea that we had every type A is some kind of blob, is some sort of topological space, right? And we have a point. If we have a point A here and a point B here, then a path P from A to B is literally just a path in this space, right? Now I wish I was better at drawing, because then I could draw a hand coming down like this. So the idea here is path induction tells you basically that you can squeeze this path. You can just put one hand on A and one hand on B and just push it down to something constant, right? So you could just push it backwards. You can pinch it, right? You can put one finger on A and one finger on B and just squeeze this path into one, right? Yeah, that's a homotopy, right? But what happens if in your space, let me try to draw the same one. That's not going to be pretty good. Oh, not so good. Okay. What happens if you have a point A and a path from A to A? Well, this idea of squeezing it doesn't really work, right? Because what do you have to squeeze together? You only have one point. So you can't just place your finger on 2 points and squeeze it along P. Maybe you can pick some point here on P and try to squeeze it. What happens then if you try to squeeze it? Well, you end up with this situation that you just get some form of something like this, right? Doesn't really work. This intuition of contracting a path doesn't really work. And this is sort of what gives rise to all the homotopical interpretations of type theory. So it's actually, I mean, it might be annoying that this principle fails and that you can't use path induction on paths from A to A, but it's also a cool thing, and it's gonna sort of motivate a lot of things later on in the course. But I hope now I should stop babbling because I don't want to confuse you with anything. So any questions or anything like that? So, sorry, yes. I can stop the recording too if